Okay, so in the previous class for this fourth order system, if you remember, I'm continuing the problem, right? For this problem of mass, and it was a spring here, it was a spring here, it was a damper here. So M1, M2, K1, K2, K3, and C1 and C2. If you remember, we got mass matrix vector x double dot plus damping matrix cx dot plus the stiffness matrix was introduced, and I said here is F1 and here is F2 equal to F equal to F. So, and the M, if I remember, it was, I said that they are equal. So let us say now they are not equal, because I'm going to go to the MATLAB. M1 and M2. And the C, if I remember, was C1, see here, connected to this 0, 0, C2. Okay. And the K matrix was, see, these are connected to the M1. So it's going to be K1 plus K2 minus K2 minus K2 and K2 plus K3. Right, everybody? Had this. And I told you that if you want to go to MATLAB, you have to write this as x double dot. Gonna be inverse of mass matrix in minus cx dot plus kx up minus kx plus f. Okay, and we have all the matrices we're going to define in MATLAB. So, and then I told you that you have to define the state variable, like as dm1 is m2, dm2, okay, and I named this in the from previous class. If I say this is a vector, gonna be a 1 and 1, dm3 gonna be m4, as you now know it, dm4 gonna be what? A 2 and 1. Remember, state variables are this. M1 was x1, displacement of this, and this is x2. M2 was x dot 1, M3 was x2, and M4 was x dot 2. Remember? And if you have the time derivative from this, dm1 gonna be x dot 1, it's gonna be m2. dm2 gonna be x dot double 1, so it means the first line of this matrix a1. dm3 gonna be x dot 2, gonna be m4. dm4 gonna be x dot double dot 2. Because remember that, if you remember that x double dot, you have your notes. was x dot double or 1, x double dot 2. Yeah, so when I say this is A, so it's gonna be A11, first line, first column. X dot double dot is gonna be A21, second row, first column. Everybody agree? Yes? Now I'm gonna give a number. I'm gonna say one is 1 kilogram. M2 is gonna be 2 kilogram. C1 damping coefficient gonna be 5 here. C2 gonna be 2. Just numbers. K1 gonna be 15 and K2 gonna be 10 and K3 gonna be 20. Now I'm gonna go to MATLAB and develop the code, because we already did the Laplace transform and the transfer function that we have fourth order system in the previous classes. Now I'm going to see if you have fourth order system, how we code this in MATLAB. So MATLAB. Yes. Modeling of high degree of fourth order system. Yes. That's generally high order systems, but here is 4 now. Okay, and we're gonna build up eventually to much higher. Okay. So let's do that together. So I'm gonna say function, as you know in the ODE, DM state variables. I'm gonna say mass spring damper fourth order system. Say fourth order system. Time and state variable. Now you know it, how to do it in MATLAB. Even in your midterm we had it, right? And I'm gonna DM gonna be space for that is 4 and 1. You have 4 state variables. I'm writing here. You have 4 state variables, right? Now you know it. If you have 10 state variable, it's gonna be 0, 10. If you have 100 state variable, 100 only. See what I'm saying? So it's 4 state variable. So yes. Now M1 I'm gonna define as how much. Read the numbers for me. M2, what was that? 2 masses. Obviously these are in the kilogram. Okay. So K1, how much was K1? I told you. Guys? Hello? I think the rest is sleeping in the class. So K2 is K2? Okay, I don't know. K1 is 10 and K2 is 10? No, K1 is 15. And the K3 is 20. Okay. And the C1 was 5 and 2. And C2 is 2. Now, what I have to do, I have to define that this A matrix, but first I have to define MCK. Okay, so matrix M, mass matrix, gonna be M1 0 0 M2. Here we go, right? Look at here, guys. If I say M is 1003, it's gonna give you this matrix. That's right. Now this is mass matrix. Now damping matrix C gonna be C1 0 0 C2. It's gonna be damping matrix, and the stiffness matrix K gonna be K1 plus K2 and minus K2 minus K2 and K2 plus, if I'm not wrong, K3, right? And this is a stiffness matrix. Yeah, okay. Now, yeah. Yes, 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 yes. Okay, so now A gonna be okay, inverse of M. So you can inv, this is the command in MATLAB. If you don't know, means inverse. Inv ms, okay, inv multiplied by, see exactly what I'm doing here. See, inv my minus cx dot minus kx plus f. Okay, guys, don't forget that we defined. I'm just doing here. X was x1 and x2, and x dot was from previous class was x dot 1, x dot 2, right? So okay, so now here minus c multiplied by x dot 1, x dot 2. Okay, guys, I want that you give me the answer. What is x dot 1 and x dot 2 based on the state variables? You tell me. What is x dot 1? Look at here. Based on the state variables. What is x dot 1? What is x dot 1 here? Look at here. What is x dot 1? This is pre-kindergarten things. You have to just target the things I'm saying and find it. What is x dot 1 here? X dot 1. X dot 1. M2. So gonna be M2. Because I'm gonna make it as a column, so you have to put this. Okay. Now find me x dot 2 from here. X dot 2. Exactly. So M4. So we did it. Oh, here we go. This is minus cx dot. We did it. Okay. Now minus kx. K matrix in x. So it means x1 and x2. Look at here, guys. So see, x1 and x2. What is x1 from here? X1. Yes, and x2. Here we go. Now you are expert of MATLAB in modeling. Okay. So we're gonna be M1. This makes M3. Remember that if I say 1 and 2, it's gonna give you this column. See? But if I write 1 and 2, it's gonna give me a vector, a row, sorry. So I hope that you know it, because I taught you. See, if you wanna make a column, just do this. If you wanna make a row, just do this. Are you already clear? And now, plus f vector. For God's sake, I'm gonna say f, as you know, is f1 external force and f2. Now I'm gonna say f1 is a harmonic force. I don't know, say sine 2t. This force is a harmonic force. And f2, I'm saying is 1, means unit step. Huh? I will change it later. Okay? So I'm gonna define it. F is sine t and 1. Here we go. This is external force. And it's in the column, that's right. This is external force vector. There we go. I'm just making a space between them. And so here you have plus f. That's it. Now you make this a that you have to implement here. dm1 is m2, dm2 is a 1 and 1, dm2 is m4, dm4 is a 2 and 1. Simple like that. So I'm going to just type it here for God's sake. So I'm going to say dm1 is state variable, as you know from the first class about the pendulum. dm2 is going to be a 1 and 1, means first row and first column, because this I'm writing here, this is a vector of 2 by 1, 2 rows and 1 column. That's right. Clear until this point? Now let's go to the rest. dm3 is m4 and dm4 is a second row and first column. Here we go. Everyone understand? Yes? Yes, everybody? So I'm gonna save this as ME430. I already selected the name MSDF. Now I'm gonna go for the solver. Okay, for the solver. So solver gonna be time first, clear all, close all. Always you do it in quotes. Means clear the workspace for everyone here. Clear all the variables that's saved, and close the all the figures for the next round. Okay. So and now I'm gonna say time is from 0 with the step of 0.1 and 10. So t and y, or t and if I said x here, no, okay. C and x means x vector is at ODE 45 and call MS DF, right? And time and the initial conditions. I'm saying that the both masses starting from 0 and 0. Okay, so it's gonna be 0, 0. There we go. Understand, everyone? Yes? Yeah. So figure 1, I'm gonna say plot time and x all the rows and 1 means that means what? X1. Plot X1 for me. Yes, go ahead. No, go to the first class. It's exactly like this. This means that give me output as the vector of x1 and x2 and the total time. If I say here instead of time t, it's gonna plot total time for me. Okay. Even in the coding of the pendulum and inverse pendulum in the beginning of this semester, I was doing this. Understand? And then hold on and plot x2 for me. Plot x2 for me. And I'm going to save it for mass spring damper, fourth order, and solve, whatever I like. But here, don't forget, guys, when you're developing ODE, then this name must be exactly the name of what? The name of M file. If they're not, it's going to give you a syntax error. But for the solver, you can select any name again. Okay? And I'll say, do a read for me, and the legend gonna be x1 and x2, and x label is time in second, and the y label gonna be xi, because you have two x1 and x2 here being plotted. Okay, so save this. Now I want to double check and debug the code. Okay, so let's what? Do we have a typo here? Inv ms m1 and m2. Let me change this as these numbers probably. What's wrong with this? What? Indexation number of the array element 2. M2, M4, M3, M1. Are you kidding me? Let me see. C2, 2, 1. Okay. Let me see. What's wrong with this? No. Where I make mistake? M1, 0, M2. Okay, everything is metrics. Okay. A is in M minus C M2 M4 minus K M1 M3 plus F. Okay. Guys, let me. Oh my god. We have four state variables. I see. M1, M2, M3, M4. Positions and velocities. When I'm teaching at the morning, this is happens. So see what happened? So we have four state variables. So initial conditions must be 4. Okay? Okay, let me change everything back to this. Okay, initial conditions. The first is the position of the M1, velocity of the M1, position of the M2, velocity of the M2. Oh my god. And here gonna be M3, okay, for the position. Okay. Now it looks like, I see. Oh my god, what's happening? Okay, now if I do that, as you see, here we go. Oh my god, I have to change it to below. Yes. Okay. So I apply a harmonic force to the mass 1 and what? And step function to mass 2. But mass 2 is connected dynamically to the mass 1. So if this oscillates, this can also oscillate, but with different amplitude. See what I'm saying? So that's why we have such a graph. This is for mass 1 and this is for mass 2. And we are naming dynamically interconnected systems. See what I'm saying? So if I increase the time to, I don't know, 30 seconds, and let me close all of these because we don't need those to be shown. Okay, and here we go. This is mass 1, and the mass 2 amplitude is much bigger than the mass 1. Okay, but it's oscillating. See what I'm saying? Okay. So now now let's change this both to step, guys. Both step. Now let's what happens. Here we go. As we expected. See, both the steps, but they're gonna have different settling values. See what I'm saying? Everybody? They have different settling values. Okay. Now, if I only make this one of them as we did in the analytical solution, one of them is only step. Again, you're going to see effect of that on the second mass. Remember for the transfer function that we derived in the S4 system and we plotted by MATLAB coding with the step function. See? Here we go, x1 and x. Only I applied a step function here. But because these are connected by the spring, this can also go by step, but with the lower value, obviously. See what I'm saying? The lower value, certain alpha value. So now you tell me, well, looking at the transient response of this system, what kind of the system is this? Underdamped, critically damped, or overdamped system? Underdamped. Yes. Great. Okay. Now, what I did, I plotted the positions of the both masses. Now let me go and now plot the velocities m3, m2, and m4. Okay, so you're gonna have a dx. Okay, dx1 velocities of the masses. Okay, so if I do that, here we go. You see that after you apply the step, okay, both gonna oscillate, but gonna settle. Velocity is gonna stop here. Why? Velocity is gonna be 0 because they are settling down to the new positions. See what I'm saying? Okay. If you apply step here, it's gonna go oscillate and stops here. So the velocity gonna be 0 after a while. The same is here. Gonna oscillate and stop here. And velocity gonna be 0. And as you can see here, where is that? Here we go. Velocity for both is gonna be 0, as you expect physically. And if I change it to as we did previously, sine of t and 1, but this time the velocity gonna be 0. What do you think? Velocity gonna be 0 after settling down? No. Look at here. See, this is velocity because the system not settling down, they're gonna oscillating forever because your external force is the sine, is a periodic force. So its velocity is this. See what I'm saying? Yes, everybody? Now I'm gonna introduce you a concept here in the coding. Phase portrait. What is phase portrait? I'm just defining here. When you plot position versus velocity of a dynamical system, we name it phase portrait. Let me go back to the notes, but then I'm going back here. When you go to the advanced dynamics in graduate school, when you go into industry, it's better that you plot your dynamics without time. Okay, so if I plot for this problem or any problem, even the electrical circuit I'm going to teach after this, okay, so it's going to be f of x1 versus x dot 1, or if I plot x2 versus x dot 2. The name of this is the phase portrait. I want to see that, or phase plane, okay? This is technical name for advanced dynamics and control classes for graduate school. I'm just exposing you. If you go to industry and your colleagues, they're plotting this, you know what's this, okay? See what I'm saying? So the phase portrait is that. So I defined here. So I'm going to say figure 3, plot all x1 instead of time versus, so don't forget the x gonna be the horizontal line and the velocity gonna be vertical line, x2, and I'm gonna say blue. This is called phase portrait. Guys, before plotting this, I wanna making you thinking. You saw that by plotting this, the both masses, they're gonna oscillate. What do you expect to see from x1 and x2 versus each other? What shape? When the both are oscillating. This is for phase portrait of mass 1. What do you expect to see as phase portrait? Huh? What do you expect to see? Let's do that together and you see. Oh, it's recording. Yeah. Here we go. Oh, you're gonna see it's going to transient response, then you're gonna see a circle. If I continue time, see? So if I continue time to, I don't know, 80 seconds, then I'm gonna put grid. Then I'm gonna put as xi is gonna be x label, and you're gonna dyi. See? So what you're gonna see is this. See, starting from here, transient response, and then it's gonna be circle. I mean ellipsoid here. See here? Gonna continue forever. The name of this is a phase portrait. Now if I magnify this, zoom in this, what is that? Oh, legend. Who needs legends? Oh, zoom in. If I zoom in this, you're gonna see that they are not exactly on each other. See what I'm saying? They are looking at each other. So if you go to the nonlinear dynamic course in the grad school, we're gonna name this as chaos. Chaos happens from the third order system above. In second order system, we don't have chaos, or we don't have quasi-periodic. These are the names that if you go to grad school, you know it, okay? This is for the mass 1, okay? Do you see this, guys? This transient behavior? This transient behavior, that happens because of that. Okay, now let us go and plot the phase portrait for the second mass. Okay, it's the second mass. So it's gonna be 3 and 4. Position of the mass 2 and the velocity of mass 2. Oh, it's gonna be this. Okay. Now if I do, oh, sorry, must be red. And here we go. Clear, everybody? What I'm doing here? And here we go. See, this is the blue line is for the mass 1. Here we have domain of attraction bigger. We name this as domain of attraction, okay? Than the mass 2, because mass 2 velocity and the displacement is much lower than that. Here we go. Okay? And this is obvious. You see that the velocity, the red line, is lower and the displacement is lower. Very good. So again, I'm plotting because this is very important that you understand. Okay? See that they have different domain of attractions. Okay. Now these happen because I apply the periodic force on the mass 1. So if I apply again step function, what to expect to see here instead of this ellipsoids? What to expect to see? Let us see. Okay, let's do that. I'm gonna change it to both step functions. Okay, there we go. you're gonna see a spiral. You're gonna see a spirals. Okay, guys, you know the spirals, that's right. Spirals like as the galaxy. Milky Galaxy is like as a spiral, that's right. In nonlinear dynamics, we have to turn with the spiral. So starting from 0 and system is underdamped. If it's underdamped, gonna oscillate, finally goes stops here. When the velocity is 0. Here is velocity, that's right. And this is second mass. And oscillates and stops here. And velocity is 0 here. The name of these is spirals. Okay? These are very interesting indication of the system nature in nonlinear dynamics. See what I'm saying? Yep, everybody. So, you know how phase portrait works. And if I only apply, remember that I apply only one of them step, okay? Because system is underdamped, it's gonna make a almost huge difference between them. Starting from 0 and 0, remember? First mass, second mass gonna stop here. Okay, oscillates, stops here. How much? 0.015 from the origin. But here is almost 0.045 from the origin. And the name of this is spiral. Understand, everybody? Yes? Now, guys, I told you about the underdamped system, critically damped system, overdamped system. If I increase the value of the C's, eventually, what I'm gonna doing based on the underdamped, critically damped, overdamped system? What I'm doing? I want to try to make system critically damped or overdamped. That's right. Let us try this. I just tried some random numbers to show you how the phase portrait changed. Oh, now in the underdamped system, your phase portrait was going to the same place, but with oscillations. That's right. When I increased the damping, I made the system critically damped. I'm not sure yet, but over damped. And if you remember, in all systems, electrical, fluid, mechanical, electromechanical, robotics, if you add damping, the oscillation goes away. You see that your system, there's no oscillation anymore. Here we go. See what I have done? Yes? And if you look at the time, see? If you look at the time, there is no oscillation anymore. X1 and X. See what I'm saying? Yes? So by adding damper, I made your system critically damped, over damped from under damped system. It means that there is no oscillation anymore. See? I just want to back to under damped system. Understand, everyone? Yes? Now, you know what? Bingo. I'm gonna copy paste here, put here, and I'm gonna say 6 order 6. This is gonna be any 6 order system. Means 3 masses, springs, and dampers. But can be any system, like as electrical. I'm going to teach in the next class. K3. You know what? I don't want to do that because I want assign this and you do it as homework. Okay. So now I did everything here. Now, if you change, I don't know, the initial conditions, for example, not all of them 0. And if I run this, you're going to have different profile of the phase portrait, obviously. Here we go. See, the initial condition has changed from mass 2, not from 0. Previously was from 0. Let me close it. Previously, all of them was 0. Means the initial position of mass 1 was 0, initial position of mass 2 was 0. But here, I'm seeing the mass is starting from 0.5, starting from here. And now again, because it's under that, I'm gonna stop here. You can do the same for this. I'm gonna say not from there, from here. Here we go. See, from 0.2, not from 0. Here we go. See, guys, from 0.2 starting. Okay. For making that clear, you can add access command from 0 to 0.7 and I don't know, minus 0.1 to 0.1. Okay, access. I'm gonna tune this later. Okay, see, this is 0.2 starting and 0.5 starting from here. See what I'm saying? I changed initial conditions for the face portrait. Clear, everybody? Now, please do at homework. I'm going to share this file with you. You have to extend it only, okay? As homework for yourself. Oh. So, if you have such a system, what's happening? If you have such a system, and you have a, say you have a spring here, you have a spring and damper here, you have a spring here, and you have a spring and damper here. Drive the dynamics of the model, insert it to the MATLAB, give some values and model it, and try to plot face portraits. K1, K2, C1, K3, K4, and C2. Give some numbers that you want, but better that you model it as an underdamped system. So here you're going to have 6 state variables, M1 to M6, each 2. 2 for this, 2 for this, 2 for this ones. So obviously your mass matrix gonna be 3 by 3, not 2 by 2. Your damping matrix gonna be 3 by 3. Your stiffness matrix gonna be 3 by 3. In our case, it was 2 by 2. So I see 2 by 2, 2 by 2, 2 by 2. Understand, everyone? Yes? And I'm gonna share the file with you. Any questions?